Good morning. Testing audio. Good morning. Okay, great. No, I kasi diba there's like a audio testing system in Zoom, and then you press like record and you say something, and Zoom will play it back. So good morning, Pastor. Let's wait for others to show up. And while I'm setting up my screen, folks. Okay, we still have a few more. Can wait maybe a minute or two. Morning to those who just arrived. At this point, while waiting for others, hopefully to join us, maybe you have some questions about, anything from Module 1 or even what we've begun to discuss here in Module 2. I would gladly answer them for you while we have this extra time first. So just unmute yourself or yeah, the chat box is free as well. Gandang umaga. Okay, for this morning session, especially in towards the middle, no, I will really ask if all of you could have your cameras open. Because this is the part wherein we are going to be using our hands a lot to analyze molecules. No? So I really want to see that you're doing it the right way. I know the camera flips right and left sometimes, no, depending on your settings. So it's fine. But at least with just with what I'm dictating and what I'm sort of doing, what you can see on camera, you can follow. Is that okay? So, okay. If everyone's ready to begin, can I get a thumbs up? And yun nga, diba? Later, we have our cams on. So if you have to brush your hair a little bit or whatever, it's fine. Okay. So in our last session, I began to introduce the fundamental concepts of the first half of Module 2, which is stereochemistry, or studying the 3D nature of our organic molecules. Not just in terms of a singular central atom at a time, like hybridization, no? So, okay, this is tetrahedral center, this is a trigonal planar carbon, this is the linear carbon, or other elements. But this time, we're looking at the consequences of the three-dimensionality of your molecule. We looked at some forms that exist because of how bonds rotated. We saw forms that had permanent differences in how their certain atoms were oriented, even though they were bonded to the same things, diba? Like the same side and opposite side forms of this alkene, the double bond, so the pi bond restricting rotation. We saw a similar occurrence when you had carbons in rings. So you had the yellow and red on the same side. Again, we can't really change the difference without breaking bonds, or having the red and yellow group on opposite sides of the molecule. And then we finally ended with looking into tetrahedral carbons, meaning sp3 carbons, and we started to check whether or not their mirror image was the same as themselves. And eventually, we stumbled upon this peculiar little molecule, okay, that had four different groups attached to each of its central carbons. And we realized that these two mirror images, they weren't, okay, the same. So we could align, let's say, the white hydrogen and the red group. Syempre, I can't. Yan, the white and the red are aligned, but we end up with the blue and the yellow misaligned. And we said that no matter how many times we try to align or misalign everything, okay, there will always be groups that misalign. So now we align blue and yellow. It's now in the white and the red that misalign. And we concluded, or we eventually learned, that these molecules with four different things attached to them exhibit a phenomenon called chirality or handedness. Now, just like our right or our left hand have specific handedness. And we learned that that all boils down to the geometry of a structure. That if a three-dimensional structure has a no plane of symmetry, meaning diba, we can't chop our hand with a mirror because it will not reflect the same way in either end. That's really the reason why your hand can be a right-handed or a left-handed hand. And that's the reason why your right hand is different from your left hand. Very similar, mirror images of each other, but they can never superimpose the same way. Are we all clear in that concept so far? Kaya? Diba? Plane of symmetry? Now, we said that one of the main reasons, but not the only reason why chirality exists or how it can exist in a molecule is by having an sp3 carbon that's bonded to four different groups. And we said that it does not have to be four different atoms. So like in the example here in our slide, we had this central carbon bonded to a hydrogen and a bromine and two carbons. But those two carbons belong to different parts of the molecule that look differently. Diba? One belonged to the blue four-carbon chain. It's labeled here as butyl. And the other one belongs to this pink five-carbon chain. So again, confirming that these, although they look exactly the same in the first part, CH2s, in the context of the whole molecule, they were actually different. Now, we also introduced another term to describe the relationship between molecules that are different from their mirror images, which means it's the relationship of your right hand and your left hand. And that relationship is that these are enantiomers of each other, or the relationship itself is called enantiomerism, which again is a type of stereoisomerism. Okay. So this is just an example. I'll skip that. But basically, it shows you that enantiomers look chemically similar but are different. So kunwari, lactic acid has two enantiomers, the plus and the minus enantiomer, or the dextrorotatory and the levorotatory lactic acid. So positive lactic acid or dextrolactic acid occurs in your muscle tissue. Diba? If you're an athlete and you work out too hard too quickly, you know that you feel that burn. You're like, I'm building up lactic acid. Yun. But it also occurs in sour milk. So yung kapag yung milk medyo napapanis na, yun na yun. Lactic acid that's levorotatory, meaning the minus lactic acid, it only occurs in sour milk. It's not what your muscles produce. No? Further emphasizing that these are two different chemicals. They have the exact same functional groups and everything, pero yun. Okay. Now, the plus and the minus sign in referring to certain enantiomers refers to how they rotate plane polarized light. So we can rotate light. Parang we can, di ba we can bend light using lenses? Organic molecules can act like lenses and bend light. Plus, okay, plus enantiomers or dextrorotatory enantiomers will rotate light towards the right, and negative or levorotatory enantiomers will rotate light to the left. So plus meaning positive angles in math and physics, if you know your angle planes, and negative means towards the left. Okay. Now, again, this happens because of presence of chirality in molecules, which ultimately means you have no plane of symmetry. So this molecule here on the right is an achiral molecule, not chiral. Kasi if you look at it closely, it does have a plane of symmetry. But lactic acid, on the other hand, is chiral. Yes, it has a chiral center, but the ultimate reason why it is chiral is because it does not contain a plane of symmetry. You cannot chop it with a mirror and get the same molecule. Now, chiral centers can be found not just in singular sp3 carbons in an open chain, you can also find them in all other contexts in which you'll find carbons, including rings or cyclic systems. So take, for example, this carbon labeled 1 right there. How would we test if that carbon were a chiral carbon? How do we test if it has 4 different groups attached to it? If it's attached to a ring. Obviously, the things that are pointing out of that carbon, not part of the ring, clear yan. We have the hydrogen and the methyl CH3. But what about the ring? How do we look at the ring in terms of looking for symmetry or looking for the different components of a chiral center? And we do so by experiencing the ring in a counterclockwise and a clockwise direction. Okay? So starting from a chiral center, and if it's part of a ring, you have to go around the ring clockwise and counterclockwise. Is that clear for everyone? So starting from carbon 1, you have to go 2, 3, 4, 5, 6. You also have to go 6, 5, 4, 3, 2. Now, here's the thing though. For this particular example, on the left, the experience of going 2, 3, 4, 5, 6 is exactly the same as 6, 5, 4, 3, 2. These are all CH2 carbons. Okay? Lahat sila magkakamukha. So it goes CH2, 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 CH2. And then the other way, the 2, 3, 4, 5, 6 is still CH2, 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 CH2. So boring. That means that these two arms of the suspected chiral center are the same, which means this carbon 1 is not chiral. And then all other carbons here, CH3 has 3 hydrogens, cannot be chiral. All these carbons with 2 hydrogens, diba? They have 2 of the same hydrogen, automatically disqualifies them from being chiral. Let's look at this chiral molecule here. Carbon labeled number 2. Okay, again, we have hydrogen, methyl, and then we have the ring going clockwise and counterclockwise. So clockwise is 1, 6, 5, 4, 3, 2, and then counterclockwise is 2, 3, 4, 5, 6. Does everyone see how the experience of going around the ring on either direction is different? Kita? So carbon 1 has a double bond O, so it becomes double bond O, CH3, CH2, CH2, CH2. Sorry, CH2 lang yan. And then 3, 4, 5, 6, 1 is CH2, 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 C double bond O. Totally different experiences. Okay? That ultimately turns that carbon number 2 chiral. And again, chiral centers are indicated by an asterisk or a star. Kaya? Crystal clear? If you have a little confusion, can I get a heart? And that's totally fine. I'd rather work through these fundamentals while you're still live here with me. Um, Gab, Maiko, Pauline. Okay. Okay. Sige. Oh, yun. Thank you. Now, here's the thing though. Humans, tayo, meron tayong right hand chiral center, left hand chiral center on our body. You even have your feet. So the same thing with molecules. Okay? Molecules can have several chiral centers each. And so one of your tasks also as a chemist or as a scientist analyzing structures is to look for us all the to come up with the exhaustive list of where all the chiral centers of a molecule are. So carbon, how do we do that? Okay, these are some of the things I like to do. I like to do a process of elimination, even just mentally. Note that all carbons that are CH2 and CH3 are automatically disqualified. How do we know if it's a CH2 molecule or part of the molecule? CH2s are the corners. So any corner, diba alam natin yung corner yan, meron dalawang hydrogen dapat yan, CH2 yan. So you can automatically eliminate those and skip those when you're looking at the molecule. Any carbon at the end, so CH2s, any terminal carbons that are the ends of branches are also automatically disqualified most of the time. Especially if they have, as you can see, they have 2 or 3 carbons each. So all terminal and all corners are all disqualified. Next, chiral centers apply to sp3 carbons. So any carbon that has a double bond or a triple bond, you know that's not sp3, diba? So gawin natin, we also eliminate anything that's touching a double bond. So all of these I'm encircling. And once you've eliminated most of the carbons, you're left with carbons that you can officially test for being chiral. Okay? And those are the ones with the asterisks here. So this one here, it has this weird branch going out of the ring. It has one hydrogen that's not being shown. So always include hydrogens, by the way. And then it has the ring going clockwise and counterclockwise. And again, the ring is not symmetrical. So the ring is experienced both ways, differently. So this is in fact a chiral center, the one for carbon, and it's the only one left. So clear, everyone, how that carbon and carbon or spearmint oil is chiral? Kaya? Okay. Let's try the one from grapefruit oil, nucatone. So we add any missing hydrogens, and then we test. Hydrogen, carbon, and then the ring going both ways. And the ring is totally asymmetrical. So clear yan. This is chiral. I'll leave the two others for you to confirm on your own, but they are chiral. Okay? Now, let's skip that. Here's the thing, and this is what I pointed to a while ago. I mean, last session. As chemists, we need to be able to determine which molecule is which, or what exactly will be the expected behavior of each chiral center. And for that, we have to be able to analyze and give label to a certain configuration of that structure. The same way that we were able to give names. Okay, we particularly have a name for this hand, we called it the right hand, and this hand, we called it the left hand. And depending on you, they have certain functions each. So ganun din, the same thing has to happen with our molecules. each chiral center will be designated as a right hand or a left hand molecule. Okay? And for now, this is the time where I'll need everyone to turn on their cameras. Okay? I need you to look at your hand. Okay? So let's take your right hand and you have to visualize that the chiral center of your hand is your palm. Okay? And that all the different things bonded to the central carbon, diba you have different groups attached to the central carbon. Okay? Those are your fingers. Your shortest finger, well, if you have it, is your thumb. Diba? So we can think of your thumb as being the smallest atom or molecule or whatever group attached to your central carbon. Is that clear? Okay. Now, I want you to try to curl or close your hand and look at the direction in which your right hand curls. So point your thumb towards you, like the one here in the slide, and try to curl your fingers toward you. Just try to look at the natural curl of your fingers. So don't try to hyperextend the other way. Just bend your joints naturally. With your thumb facing you, what direction are your right hand fingers curling towards? Is it a clockwise or a counterclockwise direction? With your right thumb towards you, in what direction are your fingers curling? From palm to tip. You can just unmute yourself so that I can hear. Counterclockwise. So it's going towards your left. Tama? Did everyone see that or feel it? You have to feel your hand, okay? So yung flow ng curve is to the left. Now try it with your left hand this time. Put your left thumb towards you and look at the natural curl and feel the natural curl of your left hand. Where is it pointing towards? It goes to your right, diba? Tama? Now look at what happens if you point your right thumb away from you. So point it towards your screen or your camera. What's the curl of your right fingers now? Ano siya ngayon? Clockwise na siya ngayon, diba? Strange, I'm not. Ayun. You can just unmute yourself. Sorry, it's hard for me to chat box right now when I'm looking at the cam. Okay, clockwise. And then try it with your left hand, counterclockwise. Diba? Now try to put your right thumb going up. Ano yung flow ng direction when your right thumb is going up? It goes away from you first, right? And then it goes back to you. Diba? Goes away from you, goes a little bit to the left, and then it goes back to you. Kita nyo? If your right thumb is pointing up, it will go away from you, towards the screen, go towards the left, then go towards you. Did everyone feel that flow? Okay, that's okay. What we're going to do now is that we're going to analyze the 3D structure of molecules using our hands because it's, for me, the most foolproof way than redrawing any molecule. Now, here's the thing. We have a name for all other fingers. But we have the thumb, the pointer, the index, the middle finger, ring finger, pinky, whatever. So we have to be able to then determine which finger on our chiral center is which. And that depends on their size. And so what we're going to do is that we're going to be applying these Can-Ingold-Prelog rules or the CIP rules to then assign priority numbers to each atom bonded to our chiral center. Or if not atom, then group. And it all depends first on your atomic number, or basically the weight or size of your atom. So the bigger the number, like the biggest finger, your middle finger, will get the highest priority. We will prioritize it number 1. And then the smaller the atom or molecule or group attached to your central carbon is, the lower its ranking will be. 4. Kaya? Or am I frozen or lost? Okay, everyone's frozen. Okay. Now, sometimes, okay, it will be very easy. You'll have a central carbon, and then attached to it, you'll have things like hydrogen, carbon, oxygen, chlorine. Diba? So obviously all atoms are different. It will be easy to rank. So the largest um, atom here is chlorine. We'll rank that 1. We know that after chlorine will be high oxygen. Slightly smaller than oxygen is carbon. And then the smallest element is hydrogen 4. Clear to everyone how we're going to rank these, how we ranked or how I ranked these atoms on my chiral center. Kaya? Okay, that's the easy part if they're all different atoms. What if they have the same atom? So like on my carbon, I have hydrogen, and then I have kunwari dito, CH3, and here it's like a CH2, CH3, and then a Cl. Okay, obviously Cl will get first place. These two are carbons. They're different, but they're both carbons, so we don't know. This is hydrogen that gets fourth place. How do we then determine between the CH2, CH3, and the CH3 on its own, which will be the higher priority or the lower priority? So part of the Kant-Ingold-Prelog rules are these parang sudden death matches or duels between similar atoms. So it's like a game of poker, and we have to list down the hand or the cards attached to each of the atoms that tied. So in our case, we have this 2 carbons. One is blue and one is pink. The blue carbon attached to it, so its game hand will be 3 hydrogens. And we will list these in order of atomic weight. But they're all the same. So hydrogen, hydrogen, hydrogen. Yan yung kanyang hand for the game. This pink carbon, attached to it is a hydrogen, a carbon, and another hydrogen. And so listing it down from highest to lowest priority, this carbon will have a carbon, hydrogen, hydrogen hand. Once we have the hands of both, we will compare it round per round. So it's not like poker that you put all of your cards down. This is like one card at a time game. So round 1, we have hydrogen and blue versus carbon and pink. Who wins? Carbon of pink gets. So this is the winner. And therefore, the CH2, CH3 group will get the higher priority 2 over the CH3 on its own. Clear? Kaya? Okay. Let's try this case here first on the left. Okay. So let's pretend these 2 carbons are caught in a tie. We don't know between first and second place or second and third place, etc. What will we do again? List down all the stuff that they have, or rather list down all the atoms immediately attached to the ones that tied. So carbon, carbon, hydrogen. Carbon, carbon, hydrogen. The blue side, we have hydrogen, carbon, hydrogen. We will list that from highest to lowest, so it's listed down as carbon, hydrogen, hydrogen. We'll play the game round per round. Round one, carbon in pink, carbon for the blue side. It's a tie. So what do? We move down to the next game. Round two, carbon for pink, but hydrogen for blue. We have a winner. Okay. Pink wins, gets the higher priority. Okay. So if this were a game fighting between who gets second and third place, then this will be priority two. This will be priority three. Okay. Ganun din here. Nitrogen, carbon, hydrogen, NCH. Dito, chlorine, hydrogen, hydrogen. Chlorine wins versus nitrogen, so this already wins the game. Okay? There are other rules for interpreting double bonds. So if your carbon, for instance, contains a double bond O, it's the same as having two oxygens. If your carbon has a triple bond to something, it's as if it has three bonds to this thing. So it has CCC as its card. Okay? And you can always go back to these slides to interpret double bonds and triple bonds, okay? But I need you to understand the theory and the goal behind the Kant-Ingold-Prelog rules. It's for us to be able to prioritize which will be our thumb, which will be the middle finger, and the fingers in between. Is that clear? It's for us to be able to number everything from 1 to 4. So let's try this out. Right off the bat, just shout it out or type it in the chat box. Which group gets priority number 1? Bromine. Tama. And which is the obvious priority number 4, the smallest one? Hydrogen. Okay. Between the CH3 and the CH2CH3, which would get one priority? So CH2CH3 will get what priority? 2. This will get 3. Okay. Again, you can apply your CIP rules to determine why. Tama. How about these ones? They're all carbon groups. Third butyl, hydroxymethyl, a carboxylic acid group, and a bromomethyl group. So in terms of round, the first one, first atom, they're all carbons. This one, see, has 3 CH3s attached to it. This one, so that's the molecule. That's the molecule C. This one has an OH. This one has a double bond O, OH. And then last, this just has a bromine. Which do you think is the highest priority here? So paano to? They're all carbons, so we all have to list down their hands. So this one is a carbon, carbon, carbon. This one is an oxygen, hydrogen, hydrogen. This one is an oxygen, 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 because it's a double bond O. So it's 2 oxygens, and this is another O. And this is a bromine, and then 2 hydrogens there. Round 1, who wins? The one with our bromine, right? Tama. Round 2, who wins? O round 1 pa lang, obvious fourth priority na si third butyl. All carbons. Okay? And then these 2 oxygens tied. So the ones with the oxygens, let's break the tie. Round 2, hydrogen versus oxygen. So carboxylic acid wins over hydroxyl methyl. That's 4, 3, 2, 1. Did everyone see how or why? Kaya? If you can already rank these, that's already the hardest you'll probably get in our subject. So if this is easy for you, you're in good terms already. Kayang-kaya na. Okay, kaya? Of heart, if you're kinda lost, or thumbs up, super confident, you followed. Okay, Ryan, let's try it step by step. Would you like, or would you like another different example?
Step by step na lang, sir.
Sige. So, fudge. I deleted everything. Ayun. Okay, so yung first thing that I did, so to just make it easier, I drew the structures themselves. Okay? So how are these are how these functional groups look. Now, what we do, since in terms of the first atom, all of these are red dots. All of these refer to these carbons here. That far, do you follow?
Yes, sir.
Okay. And since they're all carbon atoms, they all tie up. They're all they all have, the molecular mass of 12, or an atomic number of 6. So in terms of atomic number, they're all as big as each other. So tie. Sabi natin, kapag tie, we have to list down what atoms are attached to them. So take example, the third butyl group. It has 3 other carbon atoms attached to it. So I will list down those 3 in descending order, but they're all the same. That's just carbon, carbon, carbon. This hydroxyl methyl group, it has an OH group and 2 hydrogens attached to it. So its hand in descending order will be oxygen, hydrogen, hydrogen. Kaya so far?
Yeah.
Okay. And then sabi natin, double bonds or triple bonds to a certain element is as if you have 2 of those elements. So this double bond oxygen can actually be interpreted as having 2 oxygens. And then this third oxygen, which I underlined in the OH group, is also an oxygen. So yung hand ng carboxylic acid group is an OOO. And then last, the bromomethyl will be just a BRHH. And then we said, we always play the game round per round. So we will always start with the strongest hand of every branch that we're trying to compare. So in round 1, I boxed all of the first groups, which is the largest element there.
BR, sir.
See, bromine. That's why we gave bromine priority 1. And which is the smallest element there? So this is
Carbon.
carbon. So this automatically gets the smallest priority number, which is 4. And then we have 2 oxygens tied up, right? Kita mo to? These 2 oxygens.
Yes.
Okay, so we'll now play the game for round 2, just to break the tie between those 2 oxygens. So I will box the next ones in blue. Hydroxyl methyl will only have a hydrogen left to play, but the carboxylic acid still has an oxygen. So who gets the higher priority now?
Yung oxygen, sir.
Yeah, that's why we gave it the 2. And then by default, losing gives hydroxymethyl the 3. Gets?
Yes, sir.
Sabine, you have a question?
Yes, sir. Sir, why can't the bromomethyl group start with HHBr?
Because the convention, so again, these are artificial rules by these scientists. We follow it. So we have, the part of the rule is to list down the hands from highest to lowest priority. Okay? Para consistent yung analysis of all structures. We have to follow these rules strictly. Is that clear?
Yes, sir. Thank you.
Okay. Now, so now that, okay, ito na. So this is where I need your cams back again. Now that we know how to label the fingers of our molecules, we will then find a way to interpret it as if it were a hand and to know if it's now a right hand or a left hand molecule. And what, again, I need you to remember is that your thumb of either your right hand or your left hand will represent priority number 4. So priority number 4, the smallest, which is usually a hydrogen atom, will be your priority 4. And all the other all the other groups on your chiral center, we will check if it follows the curve, the natural curve of your right hand or the natural curve of your left hand. Okay? Now, let's try out this particular example here. We have a certain chiral center, and then we use the CIP rules to number everything 1 to 4. So I've done you the courtesy of numbering everything already. So the groups are imaginary. You don't see any functional groups here, but you just see the numbers 1 to 4. Okay? So what I want everyone to do, or what you will do now, is that you will align your right thumb in the same direction as the 4th priority. In this particular example, priority number 4 is in a wedged position. What does that mean? That it's going out of the screen or out of the piece of paper or whatever you're looking at this on. So I want you to take your right thumb and point it towards you out of the screen to mimic that carbon 4. In fact, it should be pointing out of the screen and a little bit towards your left, towards your own left, right? Kasi medyo askew siya eh. So take your right thumb, point it a little askew to the left, and I want you to open up your hand. Now, opening up your hand, your fingers are pointing now towards or following which priority number? What priority number are your fingers now mimicking or pointing towards? 1, 2, or 3? Pauline, you look a little confused. You follow? Kaya? Priority 1. Okay. And then try to naturally start to curl your fingers. So from 1, where is it going now? Diba? It's now pointing towards the dotted 2. And then if you close your fist, where are your fingers now pointing towards? So it goes from 1 to 2. And then if you close your fist, the tips of your fingers are now pointing towards your right. Diba? Towards 3. Kita? So with your right hand, this molecule follows 1, 2, 3. So right thumb towards you, the rest of your fingers follow 1, 2, 3. Now, because this molecule follows the curvature of our right hand, this is what we call a right-handed molecule. Okay? And the right-handed molecule is called a rectus molecule. Latin for right is rectus, or shortcutted and more appropriately called an R molecule. So we won't use the Latin name anymore. It's just called an R molecule, or at least an R chiral center. Now, let's try this naman. Again, first step, take your right thumb rather, and align it to priority number 4. Again, this time 4 is in the wedge, so it's going towards you. Straighten out your fingers. What priority number are your fingers now pointing towards? Number 3, diba? And then from 3, okay, curl your fingers again and try to see what you hit next. Saan na siya ngayon? 2. And after 2, if you close your fist, becomes 1. So it's 3 to 1. That's not 1, 2, 3. Okay? So it doesn't follow our right. Now, I want you to do your left hand. So get your left thumb and point it towards you. Open up your left hand. Again, it will start to point to priority number 3. Tama? Okay, now begin to curl your left hand's fingers. After priority 3, what is it hitting now? 1, diba? So it's 3, 1. And then if you close your left hand's fingers, it goes to 2. So 3, 1, 2. Sir, paano yun? Hindi naman rin 1, 2, 3 yun. Remember, it's cyclical, so you can just repeat. So 3, 1, 2, 3, 1, 2, 3. So eventually, it sounds like 1, 2, 3, diba? So it does follow your left hand. So a molecule that does not follow your right, or if you get the opposite of 1, 2, 3, meaning a 3, 2, 1 with your right hand, that's an S configuration. You can confirm this by this time using your left hand. And then if you get the 1, 2, 3 using your left hand, even if you have to repeat the numbers again and again, that is a left-handed molecule. Now, the Latin for left is sinister, which is also the word for evil, diba? Fun fact, they used to burn people on the stake for witchcraft if you and devil worship if you are left-handed. Kaya sinister siya. Totoo yun. So work of the devil pag left-handed ka. But yun, now, so we just call it an S molecule instead of a sinister molecule. So left-handed molecules are, yun, follow your left hand. Now, a lot of the textbooks will never teach this. It's very rare that you will see a textbook or a professor teach this technique. And they will mostly ask you to redraw molecules. In my many years of teaching the subject and seeing other instructors do it the old way of redrawing, if you draw it the wrong way, if you make a mistake redrawing the molecule, the entire structure becomes wrong and you get everything wrong. So what I like about the using your fingers technique is that you don't redraw it. You have to analyze it as you see it. And so if the fourth priority is not going towards you, then you have to simply point your thumb a different direction. If the fourth priority is going to the left or to the right, then point your right thumb to the right or to the left. Point your right thumb up, point your right thumb away from you. It's so simple. Okay? So look at this example here. What priority or priority 4 is facing what direction this time? Priority 4 dashed, hindi na siya wedge, which means what direction? It's now pointing towards the screen. Diba? So dashed lines means away from you. So take your right thumb and point it away from you. So point it towards the screen. Diba? You can do that with your right hand, or you can just do it whatever, or like you can also put it like that. So you can do that. Okay. Okay. So with that, okay, if you do this, your fingers can be going up. That's priority number 2. Diba? You start to close or curl in your right hand. That's priority 3. Before pointing towards you, priority 1. Or if you do it like this, you can start at 1 before going up to 2 and then closing to 3. Kita? Did everyone get a 1, 2, 3 with their right hand using this molecule? Sorry. Kaya? Or a 2, 3, 1, 2, 3, or a 1, 2, 3 mismo. Okay? So did everyone get that this is a right-handed molecule? Julian, Michael, Alistair, Kaya? Okay, great. Okay. Oops. The molecule in the previous slide followed the right hand, and that's why it is R. But what happens when we switch any two groups? So in my case, I decided to switch 2 and 3. I took position 2 and 3, and I switched their positions. What happens to the configuration? which is the same as what if you make a mistake in drawing a molecule? You accidentally switch two things. What happens? Is it still an R? No. It becomes a left-handed molecule. So if you try your left hand, guys, left thumb, priority 4, that should be pointing away from you, your left thumb. If you open it lang flat, that's priority number 2. Then start to curl your fingers. It will go up first to 3 before going down to 1. So 2, 3, 1. 2, 3, 1, 2, 3, 1. Diba? Maganon kayo. So that's a left-handed molecule or an S. And as a rule of thumb, switching any two groups automatically switches the configuration. So the moment you already see one structure and it has already been annotated for your convenience, if you switch any two, switch the two solids or let's say interchange the dash and the wedge. If I turn 4 into wedge and 1 into dash, it also automatically switches the configuration. So R automatically becomes S, S becomes automatically R. And again, this just goes to show you that if you make a mistake, let's say you switch the dash and the wedge, or if you accidentally switch where the hydrogen is placed, you can easily make a mistake. And that's why I don't like the old book techniques of redrawing a molecule and changing dashes and wedges. So you tend to make mistakes. Okay, let's try this molecule now. First thing we have to do, anong gagawin natin? Anyone? Sabine? Well, I don't see anyone doing it. R thumb towards screen. Tama. Good job, Pauline. And with that, your right follows, the numbers follow which hand? Or does it follow your right hand rather? So try to direct your any fingers to priority 1 or 2 or 3, whichever you're comfortable with, and then curl it. Ako, easy for me to do my right hand going up. This is my right hand half. And the curl of my fingers going towards the side to 2 before going to the front to 3. So, does it follow your right hand? Kaya. So, thumbs up if yes, heart if it doesn't. Okay, good. Now, there are other examples here that you can try. Or like this one. This time, 4 is in the solid line, which means it's on the plane of the board. So what direction would you point your thumb this time? Tama, Pauline. Just vertically up. So you point your right thumb vertically up. If you put your finger straight, it points towards the screen. So that's priority number what? So if you point your right thumb up and put your fingers out, your fingers are going into the screen. That's hitting priority number 1. Start to curl your fingers. What priority does it try to, what does it begin to hit next after 1? Goes to 3 first before 2. So 1, 3, hindi siya 1, 2, 3. So it's not a right-handed molecule. Confirm with your left. Let's try it out with our left hand now. Left thumb up, fingers out to priority 1. The curl of your left hand is now going towards which molecule? 1, 2, 3. So this is an S molecule. Kaya? Now, whoa, okay. Yes. Now that, okay, you know how to get R and S. Okay. You should be able to do items like this. So this is the real deal already. This will now ask you, one, find the chiral center. Diba? So hahanapin nyo carbon with 4 different things attached to it. The second step for a problem like this, once you find those chiral centers, you will then begin to assign priority numbers to what's attached to your chiral center, right? And then the last step is to check with your hand whether they're arranged following your right hand or your left hand. And so that's how you'll be able to assign an R or an S configuration to each chiral center. And all of this you should do within 1 minute or so, because this is usually just one part of analyzing a molecule. Okay? So by the midterms or finals, dapat expert na kayo dito. Kaya? Okay. So practice, the answers are in the next slide anyway. But yon. Now, there are more to optical isomers than just this. In fact, I know we're a little over time, but the rest of it is something I think you can already study on your own. And this basically introduces the relationships or looks at the different relationships of other molecules. So if one molecule is an R molecule, its enantiomer will be an S molecule. And then we said that molecules can have more than one chiral center, which means a molecule can be an RRSS molecule. A molecule can be an SSS molecule. Diba? So if you have an SSS molecule, its enantiomer should be an RRR molecule. Clear? But what if we have the same parts, the same bonds? One molecule is SSS and the other one is SRR. So half of one part is the same, but 2/3 of the second molecule is a mirror image. So what do we call these 50, mix of mirror image and same molecules? So these are things that you will encounter in the final parts of this optical isomerism lecture. And I think you can study that on your own. But I'll try to finish the topic on Monday. Okay? Sige. Maraming salamat. And as always, if you have questions, feel free to stay behind. I have like a minute or so. If you have no other questions, feel free to leave. Okay? Maraming salamat. And I hope you guys enjoyed this session, weird as it was. Okay. Yeah. Thumbs up. Yeah. Oh, it's fucking trademark. Sorry though. Hanap kayo ibang organ, prof. Wala kayong mahanap na right-hand rule. Sige. Bye. Pauline, you have a question?
Sir, sa Monday pa rin po yung quiz.
What quiz? Sorry?
Ay, sabi po kasi dun,
Yung
end of
Yung module 1. Yeah. You still have to make sure your module, the deadline is already set there in the module quiz itself. So if it's late, it gets 20% deduction. But you can still pass it.
Okay po. Thank you, sir.
Okay, bye-bye.